Okay, welcome back. Starting with part 3. So the question really is the proof that harmonic series being divergent, is it really the first time we see a proof for such theorem? And the answer is no. Not that Bernoulli was actually aware of this, but there were two other mathematicians. The first one was Nicole Orismy, a French scholar, some 3 centuries before Bernoulli. He actually is the first known mathematician to prove that the harmonic series are divergent. And the next one, and he predates Bernoulli by some 4 decades or so, Pietro Manoli, Italian mathematician. And we shall give here another proof due to Manoli, and it's also just as nice and simple proof, but rather different from Bernoulli, Johann Bernoulli's proof. So we'll proceed with this. Before I write Manoli's proof, I must state and prove a little theorem that is the main ingredient of the proof of Manoli. So, Pietro Manoli. And the first little fact that he used in his theorem is the following. If we have some number, and that number is greater than 1, then it is true that 1 over less than that number plus 1 over that number plus 1 over 1 more than that number, the sum of these 3 is actually greater than 3 over that number. Okay, so we'll prove this result first, and then we'll move on to proving or giving a proof of Manoli's that harmonic series diverges to infinity. Okay, so for this one, proof, we'll begin with the following obvious facts. So begin with the fact that whatever number a is, 2 times that number to the 3rd power surely is greater than 2 times a to the 3rd power minus 2a. So if you have a quantity, that will be greater than that quantity minus something smaller than the quantity itself. So this surely is true. 2a to the 3rd minus 2a is in itself equal to 2a if you factor out 2a with a squared minus 1. Okay, so we are here. 2a to the 3rd we're saying is greater than 2a times a squared minus 1. We have an inequality here, and you can divide both sides of this inequality. So divide by both sides, obviously, by a squared times a squared minus 1. So we have 2a to the 3rd over a squared times a squared minus 1. That is greater than 2a times a squared minus 1 over a squared times a squared minus 1. So let's see what we can cancel here. These 2 cancel. This a cancels with 1 of those, and this cancels with 2 of those. So what we left with is 2a on the top on the left hand side over a squared minus 1. Turns out to be greater than 2 over a. You have 1a factor left here on the bottom, so 2 over a. So we're going to use this. So we're saying the following. So 1 over a minus 1 plus 1 over a plus 1 over a plus 1 is equal to, let's regroup this, 1 over a minus 1 plus 1 over a plus 1 over a plus 1. Here in this grouping I will put things in the same denominator. So this left hand side is equal to 1 over a minus 1 plus, if you, a little bit of algebra, if you put things on the same denominator here, you will have, oh, this is, I'm sorry, I meant to say 1 over a plus 1 over a minus 1. My mistake. So the same denominator here would be multiplication of this 2, and these are two conjugates multiplied together. They give a squared minus 1. So on the bottom I will have a squared minus 1, and on the top, after some very, very simple algebra, you'll get actually 2a. Okay, so we're saying that this left hand side is equal to 1 over a plus 2a over a squared minus 1. But this quantity 2a over a squared minus 1 from this previous step is actually less than 2 over a, which makes this entire side greater than 1 over a. This goes along for the ride, and since 2a over a squared minus 1 is greater than 2a, I write here greater than, not equal, but greater than 1 over a plus 2 over a, and that is equal to 3 over a. So I'm saying that the left hand side is actually greater than 3 over a, which was to be proved. So much for this little result. Now we're getting back to the statement and proof of the theorem again. So again, the theorem is the same, and as I said before, this is due to Manoli. So harmonic series diverges. Harmonic series diverges. Okay, so proof. Let again, let H be the sum of harmonic series. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on. So here I'm going to actually regroup things a little bit, and I can do that. So not regroup, but group rather. Plus I will add 1 over 2, 1 over 3, 1 over 4 together. And then the next three ones, so 1 over 5 plus 1 over 6 plus 1 over 7, and I'm going to investigate that, plus 1 over 8 plus 1 over 9 plus 1 over 10 plus 1 over 11. Keep in mind this goes on to infinity, so it's perfectly okay for me to keep writing these blocks of sums. 1 over 11, 1 over 12, 1 over 13, and so on. Okay, well, so this means that H is equal to 1. Well, it's not actually equal, it will be greater than 1 over 2, 1 over 3, 1 over 4. By this theorem, should be, each of these sums should be greater than 3 over the middle number, if you will. So this is the same as 1 over a minus 1, 1 over a, 1 over a plus 1, where a in this triple is 3. So according to that theorem, this first triple is greater than 3 over 3. So this other one, the middle number is 6. You have a 5 and a 7 here. So again, according to that theorem, that will be greater than 3 over 6. The next one, the middle number is 9. So according to the previous theorem, that would be greater than 3 over 9. The next one would be 3 over 12, and so on, and so on. Well, okay, let's see. H is greater than 1 plus 3 over 3 is 1. 3 over 6 is half. 3 over 9 is 1/3. 3 over 12 is 1/4, and so on. Well, so that means that H itself is greater than 2 plus, well, if I look at these three numbers, I keep recycling the very same result from a little before. Again, here the middle number would be, the middle denominator will be 3, which will make the sum of these three things greater than 3 over 3. And the next one, if I was to continue with this, the next one would be 3 over 6, 3 over 6, so this is the sum, 3 over 6 plus 3 over 9, and so on. This keeps repeating, so h is greater than 2 plus 3 over 3 is 3, plus 3 over 6 would be again half, 3 over 9 would be 1/3, and so on. So you keep doing this, each time you keep collecting 3 terms that will be of this form, and you never actually, this can never actually sum to anything finite. So h, so we're saying that, so h exceeds 1, 2, 3, 1, 2, 3, 4, and so on, because each step tells you that h will be bigger than 3, bigger than 4, bigger than 5, bigger than 6, and so on. So exceeds 1, 2, 3, 4, and by repeating this, let me just write this nicely, and by repeating this, process, I mean, will exceed any finite quantity at all. It will exceed any finite quantity being the key word, at all. Hence, h is divergent. And that would be the end of this proof, and end of the part 3, and end of lecture 11. Watch out for the homework assignments. This time will be from the list of problems, and until next time, everyone.